السلام عليكم دكتور.
Assalamu alaikum. So we will start today chapter 3.
دكتور
I have already given the. Do you have any question about the lecture?
لا أنا عندي مشكلة هي الامتحان. نعم.
يعني أنا قاعد أسجل حق lecture, okay? So nobody ask me about anything else, please. So let us start. Well, today chapter 3. I've given you chapter 3 and 4. I already put it there in the files for you and the teams. So in chapter 3, we're going to do, we are going to look at the structure of crystalline solids. So let me use this one. The structure of crystalline solids. So what is the structure? Of course, the definition of the structure you already know. So we want to know what is the structure of crystalline solids. And specifically solids we are talking about. So we will, in this chapter, so we'll not be dealing with liquids or gases. So this is what we are concerned with. We will look at, in this chapter, at crystalline versus amorphous structure. We already did something.
دكتور
Yes.
السوليد والجازز بناخذهم في شابتر الغير والله مو في الكورس كلش.
We are concerned with solids actually. We're not concerned with liquids or materials. We're not concerned with liquids and gases. So I said the point that we are going to deal with solids because the student need to focus that we are dealing with solids. Sometimes the brain goes somewhere else and he thinks about gases or so on and so forth. Okay, so we are dealing with solids. This is what I'm saying. So we already dealt with crystalline and amorphous structures. We are going to revise that again. And then we are going to look at the crystal structure. What are the features of a crystal structure? We will be defining and looking at what unit cell means, the lattice means, the types of crystal structure. There are different types of crystal structure. The meaning of the crystal structure, simply what does it mean? There are things that are important in every crystal structure, like the coordination number, the close pack directions, the atomic packing factor, which we refer to as the APF. And then finally, we will be skimming through what we refer to as the crystal systems. This is what we are going to do in this chapter. So before we start, let us see why we are doing that. What's the goal, actually? Like I'm putting it there as a motivation. We know from the previous knowledge that we have learned that what is one thing important which affects the physical features of the material. We are concerned about physical properties, mechanical properties here. So one of these things that we have learned is the atomic bonding. The stronger the atomic bond, it changes the property of the material. Melting point temperature increases. Stiffness of the material becomes more, isn't it? The bonding of the material changes the property of the material. If you add refractory elements, for example, to any material, to any ferrous or non-ferrous, actually, we can say that metals, it increases its strength. It makes it stronger. So atomic bonding is one important aspect which makes the physical properties of the material change. So in addition to atomic bonding, the physical properties of the material, so I'm already mentioning the atomic bonding because we have already covered that, depend also on something else. There is some, number two, there is another thing which also the physical properties depend in general. And that is the way atoms are packed together or arranged together. So how the atoms are packed together, how they are arranged in lattice, how they are ordered in lattice, this is another thing which affects the material mechanical or physical properties. So many properties of materials, especially the mechanical, are determined by the arrangement of the constituent atoms. How the atoms are arranged or ordered, this arrangement of or ordering of the atoms in a space or lattice, let's call it for now, is this arrangement is called the material's crystal structure. The crystal structure of the material affects the mechanical properties of the material. So there are two things, as we are saying. The atomic bonding, first of all, and then we have what? The atomic bonding and the crystal structure of the material. So what is the crystal structure basically, or simply speaking? This crystal structure is the way atoms are ordered or arranged in space. How is this? And this is not unique. The arrangement of the atoms in space is not unique. You have more than 14 ways, not 14 ways, more than 14, 15 or 16, more than 15 or 16 ways the atoms arrange themselves in the space. And we are going to look at the most important crystal structures. Also, we will see how atoms arrange themselves or order themselves in the lattice or the space. So before we proceed, we need to make just a small but important distinction for the student also to understand what we are at here. When we talk about atomic structure, when you read in the chemistry, you see atomic structure. This is what is referred to as an atomic sublevel. So this is subatomic level, actually. So this atomic structure relates to what an atom consists of. It relates to the number of protons, neutron, nucleus of the material, and the electrons, and how they are connected together. This is what we mean by atomic structure when we look at that. That's a subatomic structure. In the crystal structure that we are dealing with, on the other hand, the crystal structure is not a subatomic level that we are looking at. It pertains to the atom arrangement of the atoms in the crystalline material. It is not subatomic, it is atomic structure. So it is one level beyond the subatomic structure. This I just normally want to clarify that point in order for the student to be clear with which level of a structure we are looking at. It is the atoms arrangement in space. It's not the subatomic level that we are dealing with. So let us start with briefly reviewing what we have already done previously. We said what is crystalline materials and to compare that with the amorphous materials. Crystalline materials are materials in which atoms are packed in periodic 3D array. So this is a crystalline arrangement. You see that arrangement repeats in the material everywhere. 3D. This is the crystalline silicon oxide. So if you have a repetitive, generic, periodic 3D array which repeats in the entirety of the material, this is called crystalline material. If you have a long range order or form or periodicity, this is called a crystalline material. Examples or typical materials which display that are the metals, of course, all the metals. We have many ceramics, actually we can say most of the ceramics, except for the glasses. Glasses are amorphous. And some polymers as well display this behavior, crystalline. What are those polymers? Do you remember? Which polymer displays this? Cutting short the story short, we want an answer, but nobody's answering. Like the
thermoplastic.
Thermoplastics. Some of the display some feature of crystallinity in the material. On the other hand, non-crystalline materials have no order. You can see this is different than this, and different than that, and different than this. There is no periodic, generic, repetitive in the 3D array or 3D array that continues in the material. There is none of that. There is no long range order or form in the material. So atoms have no periodic packing. And it occurs for complex structures. You have very complex structure there. And it occurs due to rapid cooling. Sometimes it occurs also due to mechanical working as well. It causes this non-crystalline structure to form. This is an example of, again, silicon oxide. And this is crystalline silicon oxide. This is non-crystalline silicon oxide. So therefore, non-crystalline, a word for the non-crystalline, you can fill up the dotted lines here. You can say amorphous, means non-crystalline. Atoms can be arranged either in regular periodic array, for example, it has long range order, or completely disordered, which we refer to as amorphous material. This is a revision of what we have done previously. Now, let's start talking about the crystal structure. How are we going to deal with the crystal structure? We need to set the scene first of all. أول شيء نبرز المسرح, يعني set the scene before we start our story with the crystal structures there. So to start with, we use what in the explanation of the crystal structure, we use something called the hard sphere model. And this is an assumption that we do, in which that we deal with the atoms, or we think of atoms that they are thought of solid spheres with the spheres touching each other. This is what basically we assume. Atoms are not solid spheres, صح? Because most of the atom is empty. So there are electrons and there is a nucleus in the middle. Most of the mass is there inside the nucleus, the neutrons and the protons, and the rest is mostly empty. You have electrons there. But to ease the matter of imagining the crystal structure and how things are folded together, we assume that the atom is a solid sphere. To illustrate the concept of crystal structure and lattice systems, we first identify, so once we adopt that assumption, we say this is our assumption, then we also need to define the coordinate system. We say that our x, y, and z. As you can see here, if this is my cubic, now I'm looking at a cubic structure here. So we define our x and our y and our z. Why is this important? Why am I mentioning this? So we could say y and x and z, or z and y and x. We could say that, well, that you could do in your statics course, in your dynamics course. But here in material, you can't do that because we are basically concerned with the directions here. In the statics course which you have done, you were concerned about applying equilibrium equations. You remember equilibrium equations, or you didn't take statics yet? You remember that? How you were applying? You were saying summation of the forces in the x direction is equal to 0, right? Then you need the coordinates to know which one is the positive direction and negative direction. So the forces in the positive x direction are equal to the minus the forces in the negative x direction is equal to 0. So those directions are set actually, or assumed, in order to do that equilibrium. And also then you had to do summation of the forces in the y direction, and similarly summation of the forces in the z direction, and so on and so forth. So those directions which were assumed, they were arbitrary. Meaning what? Meaning that you could do x here and y here and z here, or y here and z x, y here and x here and z here. Those were arbitrary. It doesn't matter. There is no point. There is no problem. But in our case, it will be different, because when it comes to identifying the directions there, you need to keep the x in this direction and y in this direction and z in this direction. If you change them, if I change it And Muhammad, if Muhammad takes it like this, and I change them to Y and X and Z like that, then we will be talking about different things, different directions. So because we are concerned only about directions here. So that's why we need to set our system. Everyone sets the system to X, Y, and Z in the way I'm showing there. So it's not arbitrary. Now, next, what we do, we place an atom at each corner of that cube which we have. And basically this, since it is a cube that we are drawing, because not all the crystal structures are cubic, but we start with the simple one. We place a hard sphere, which represents an atom at each corner, as you could see there. Now this represents a hard sphere model of a cubic crystal system. This is a cubic crystal system. In reality, we want to look at it like that. Atoms touch along the crystal axis. These directions and these directions which the atoms touch one another is a special direction basically, and we will come to that in the next slides. And these directions are referred to as the close path directions in the simple cubic system. This is called simple cubic system. So the name of this crystal is called the simple cubic system, and those directions are referred to as close path directions. Why close path directions are important, we will come to this in the next slides. What is an example for the simple cubic crystal structure? A material which displays, this is what I'm looking at, a material which displays the simple cubic crystal structure which we are looking at is the polonium. You can find it in the periodic table there. Polonium is the only material which I know which displays the simple cubic crystal structure. So the above diagram represents a simple cubic crystal structure. Crystal structure. A simple cubic crystal structure. This is, and simple cubic crystal structure normally is abbreviated by SA, like that. Simple cubic, SC. So this is abbreviation for the simple cubic. In the simple cubic crystal structure, you have one atom in each corner only in the cube, like a cube, and this is how the atoms are arranged. This is how the atoms are ordered. So this is the crystal structure of the material. This is what the meaning of crystal structure is the arrangement of the atoms in this space which we are looking at. There are other terms that we need to employ when we are studying crystal structure, when you read your book also. So you need to know those before we start looking at the crystal structure, like the lattice, for example. What's the meaning of lattice? The lattice is the three-dimensional array of points coinciding with the atoms or the hard sphere centers. So if we're looking now at all that, of course, this is inclusive the atoms which are there, but the lattice are the positions of the atoms only. If you have only the lattice there, you would see only those points which I'm drawing now. So if those points are drawn only, this is called the lattice. And so therefore the lattice means what? Is the positions of the atoms in the space. Those are called the lattice. The lattice for a BCC crystal structure is different than the lattice of a FCC or simple cubic or hexagonal closed packed crystal structure. So this is what the lattice basically means, are the positions of the atoms in the space. And another concept or term which we also require to understand, which is called the unit cell. What is the unit cell? The unit cell is the smallest entity that exhibits the chemical and physical properties of the material. And pay attention to the smallest entity. Suppose, for example, we have a wall. A wall, any wall. You need, you have a if you are sitting in a room, there is a wall, isn't it? There is a wall. A wall is made of what? What is the wall made of? What's the wall is made of what? Of blocks, صح?
إيه طابوق.
Am I explaining? Are you with me, guys, or you are all asleep?
وياك دكتور.
with the دكتور.
Okay, with me. So if we wanted to know the properties of the material here in this wall of your room that you are there, which is made from, you are making it from blocks, صح? من طابوق. Okay? So if we want to know the properties of this material, of this wall basically, what can we do? We can take the wall and test it, and we put it under tension or compression there. صح? All the wall, we can put it under tension and compression. We sample all the wall here, a big wall, and take it, we sample it, and we take it to the testing machine and test it. And we can know the properties of that. So we can study the wall in this way. Or otherwise, we can do something simpler. We can look at a block, one block only, طابوقة واحدة, one of the blocks which we have there, and we can pick it up and sample it out, and we can test this block only. And we can put it under tension or compression, if you, whatever you want to do. Of course, this is a ceramic material. You normally don't need to do tension to it because it's brittle, so you do the compressive test there. So if you want to study the whole wall, you don't need to study all the material there. You can study a small entity, or the smallest entity, which will represent the whole material, both in chemical and physical properties. So if it is possible to extract an entity from the material which will display or exhibit the chemical and physical properties of the material, then we do that. This is called the unit cell. Of course, this is on the macroscopic scale we are talking about. For the crystal structures, we will be talking about nanoscale. We will be looking at nanoscales here. Then instead of studying the whole lattice like this, we can just simply choose a crystal structure, a unit cell. Let me make the marker bigger for you to see better. We can just model a small unit cell there, the smallest entity, which will represent or exhibit the chemical and physical properties of the whole material. So if we can do that, of course, in the same way, this simplifies the matter and makes the study of one block much easier than studying the whole block. We will be getting also, it will be much easier to study a unit cell instead of studying the whole lattice. So this is the idea of the unit cell that we want to use, and we will be using in the crystal structures there to study, define and study the different features of different crystal structures. Unit cells are the most elementary arrangement of atoms, which we refer to as the building block. Remember, and I brought this word building block, which can generate the entire crystal structure. So you can generate the entire crystal structure by just copying that everywhere, or mirroring that, or whichever way. So you could use, you can generate the entire crystal structure upon application of suitable translation, rotation, mirror, inversion operations. You can produce the whole structure again. Unit cells for most crystal structures that we are going to deal with are parallelepipes or prisms having 3 sets of parallel faces. So we have basically cubic, we could have hexagonal close packs, so we can have hexagons as well shapes. We will see the different examples of that. So this is basically the point of covering what we refer to as the unit cell. It makes life much easier. This is a concept which I use also, and nowadays we have what we refer to as micromechanical modeling. This is an important concept that we use in a lot of applications. That starts with it starts with the material actually. The definition of the unit cell is there. The length of each unit cell axis is called the lattice parameter. So if we have the unit cell of whatever shape, of course, this is our, we are just putting it like that so that we have different angles. The length, those dimensions there, this, and that, are called the lattice parameters. Also, and of course, so in simple cubic systems, all the three orthogonal lattice parameters are equal. So if we have a cubic, of course, you know that cube has the same dimension. This dimension, that dimension are equal. Lattice parameters are typically in the order of angstroms. So for you to be clear about what we are looking at, so that those dimensions will be what the level of dimensions, since we are talking about atomic, not the subatomic, but the atomic, it could be few angstroms to nanometer. So this is the dimension that we are looking at basically. 1 times 10 to the minus 9, or a little bit less, or few of those, few angstroms, so it will be that. In addition, the other lattice parameters are the three angles. So if you have, this is one angle, the gamma and the beta and the alpha. Of course, for the cubic systems, those angles will be equal. Again, in the same way, the other lattice parameters were equal. So in the cubic system, the length of the lattice parameters are all equal, and the angles are all 90 degrees. They are not different. They are 90 degrees. Now, before we proceed, also we wanted to just have a look at metallic crystals, a note on that, and something which we observe actually in the material, and that is that metallic crystal structures tend to be densely packed compared to the other structures of materials, and we are talking about solid crystals here. Come on. Metallic crystals tend to be densely packed. Densely packed, the density is much greater than the other materials, so their weight is way higher than the other materials. And if you compare the metals to ceramic materials or to polymeric materials, for example, you can see that the metals are much more denser than the other materials. The weight is much greater. Why does this happen? There are several reasons for that. Typically, one of the reasons, from what we have already studied, that only one element is present. So all the atomic radii are the same. And if you are having the same size, packing will be much easier to pack in a room, for example. Suppose that you have boxes of different sizes. Boxes of different sizes. Many boxes of different sizes there. And you want, of course, many of different sizes that you have there, and you want to pack those in one room. Imagine you have the corner of the room, you want to pack them there. ترتبهم. تملي الحجرة. Will there be any gaps there in the room? Yes, there will be, because the sizes are different, so indefinitely you will have some spaces there, here and there. But if all the boxes have the same size, the same dimensions, will there be any gaps when you pack them in the room? I'm expecting you to say no, of course. ما بيكون فيه, صح? So the packing will be much easier with no gaps in between if the dimensions are the same. And in metals, typically only one element is present. يعني in iron, in steel, for example, typically we have the overwhelming majority of the atoms which we have there in the steel is iron. There is a little carbon, and carbon does not take any the role of bonding actually in the steel. There are some other alloying elements that we are putting there. These are considered to be small amounts, and these are considered to be imperfections in the material, but the rest, overwhelming majority of the atoms, can pack themselves much better. So that's why, this is one reason for why they pack themselves much better, since you have a single radii there. Another reason is that metallic bonding is not directional. Metals, unlike, let's say, ceramic materials, unlike polymeric materials, the polymers have chains of different materials. You can say carbon with hydrogen, and I'm not going to continue the structure. And then you have, for example, this is polymer. You have in the ceramics, you have silicon oxide, magnesium oxide. So you have the magnesium and you have the oxide, oxygen. So you have two things there of different sizes also. These are of different sizes. As we have said here, you have typically one element. These are not one element. These are two or more elements available there. SiO2, for example, it could be that. A magnesium oxide, and so on and so forth. So packing will not be good, as we have said in the first point. But also, in metallic bonding, the bonds are not directional. Meaning what? The bonds in the metal, as we have explained before, is that we have the atoms there, and among the atoms we have free electrons. We have a sea of electrons. I'm not going to draw the whole thing. I don't want to draw the whole thing, but my hand is not stopping. So let me continue that part. So I forgot to bring my pen, otherwise it would have been much easier, because I'm using the mouse here. And set the pen molly. So anyways, and we have what? Color. Okay, oops, and we have a sea of electrons. Hopefully it is clear. And we have a sea of electrons everywhere. Where did these sea electrons? These are the free electrons, right? So the bonding between the atom, the core, and the other things is due to the charge. The electrons are negative and the cores are positive. It like glues in the cores together with this charge. It's very similar to magnetic. Like if you have two magnets here and there, then there is a magnetic force between them. Will this atom, or will this object, let's say object now, since we are talking about magnetic, does this object need to be in this direction only, or it can move in any direction there, and there still the magnetic force will be there, right? So in the magnetic force, it's not directional. It can move. You can move around the element or the object in any direction. The force is still there. The same thing for the atom, for the cores, and for the metallic bonding here. It's not directional. You can move. The atoms can move in any way, and pack itself better. Unlike the other materials there, the ceramics, or the polymers there, for example, you have covalent bonding here. And this covalent bonding, you have a bond here and a bond here, for example, and a bond there. So this atom, if it wants to pack itself where it needs to move, well, to move, there is something binding her here and binding her here. So there is a bond. Even in the ceramics, which are ionic actually, and depends on the charge there, but still you could have a directional because it's being pulled by something else in the other direction. The pole is here, the negative sign is here, and the positive sign, for example, is there. They are pulling each other. There is direction there. But in the metals, there is no direction basically because it's a sea of electrons the cores are swimming in. So they can roll around, they can move in any direction, still the bond is not affected. So this is why atoms in the metallic, due to the metallic bonding in the metals, are not directional. They can rotate, they can sweep, they can move in any direction, and the bonds is not affected because the bond is not directional. So this is one reason for better packing than the other materials in the metals. The last thing, the nearest neighbor distances tend to be small in order to lower the bond energy. Of course, that is generally applicable for all materials. And this is what happens. Since it can go for lesser distances to the distance where you have the material at its lowest energy level, it's going to do that. So basically, all of those which are available in the metals basically make the metals behave or tend to be more densely packed than the other materials. This is what, based on what we have studied so far, we are explaining why is it that metallic crystal structure tend to be more densely packed than the other materials. Now, let's start talking about the crystal structures. We are set. We have set the scene. Now we can talk about the crystal structure. We have the simplest crystal structures there that we are going to look at, and we will be looking at the three most commonly available crystal structure found in the metals. Yani we will not be dealing with all the crystal structures. We will be dealing with the most commonly ones which are there. Of course, as I said, there are more than 15 or 16 different crystal structure types, but we are going to deal with in this chapter with the most important ones, in addition to the simple cubic crystal structure, which is not very most common. Why? Because the one that we have dealt with here, which we have shown, is for the polonium. We said it's the simple cubic. Where is the mouse? Is and it's very rare actually, the simple cubic. We find it in the polonium only. So this is called the simple cubic crystal structure. We're also going to cover that, but it's not the most common ones there. The simple cubic is not the most common one. The three most common ones are the body center cubic, which we abbreviate with the BCC crystal structure. So this is the abbreviation for that. The short form we refer to as the short form, body center cubic. So let me use the pen again here. So this is the body for the first letter here, body, and then center, and then cubic crystal structure. You need to know the short form and you need to know the full name of these crystal structures that we are dealing with, also the simple cubic as well. And the second type of crystal structure is the face center cubic crystal structure, the FCC crystal structure there. And the third type of crystal structure is the hexagonal close pack crystal structure, the hexagonal close pack, the HTP crystal structures. So let us look at what we are concerned with and what are the features of the different crystal structures. There are features which define crystal structures and important for the crystal structures that we are going to deal with, like the coordination number, the close pack directions, and the APF. These are important characteristics of the crystal structure. So the three most important characteristics of the crystal structures are these: coordination number, atomic packing factor, which we refer to as the APF, and the close pack directions. What are those? Just we will try to simply define them. Then we are going to find those actually on the different crystal structures that we have. to digest these identities. So the coordination number, what is the coordination number? It's basically on simply the number of nearest neighbor or touching atoms. So this is what it is. How many touching or neighbor atoms are there in a crystal structure to any of the atoms? This is what we refer to as the coordination number. We are going to find it, of course, for every crystal structure which we are going to deal with. The second thing, it is the atomic packing factor, which we refer to as the APF. The APF, the atomic packing factor, is the volume of the atoms in a unit cell divided by the total unit cell volume. يعني شنو؟ يعني how it basically gives an indication of how filled, or you can say how empty is a crystal structure. So if you divide the volume of the atoms, if you have a unit cell, you divide the volume of the atoms by the volume of the total unit cell. This means you are looking at the percentage of the occupancy in the atom in terms of of the unit cell in terms of the atoms. So how much packing, the better the packing, the less the emptiness, the less the void area, the less the more the atom volume there. So the higher the value of the atomic packing factor, the denser the material will be, basically. So this is another thing that we are going to also calculate that. And the third thing, the third important thing there also, it is the close pack directions. Close pack directions are the directions at which the atoms are closest to one another without a gap. Why are these directions important? It is important to know which slip directions are there in the crystal structure. So why the close pack directions are important? Well, basically because the more the number of the close pack directions, the easier it is for the dislocation to move, the easier it is for the plastic deformation to happen, the weaker the material will be. So the dislocations which we refer to in the explanation of the plastic deformation does not move in any direction. Basically, it moves in specific directions in what we refer to as preferred or favorable directions. What are those directions? Are the close pack directions. We will come to this and explain it in more detail, but for now we just wanted to highlight the characteristics of the crystal structure which we want to study. We will come to that again. In addition to those three things, in order to calculate some of the, like the APF, one of the characteristics, we need also to get what we refer to as the number of atoms per unit cell. So for each of the crystal structures, we need to determine the number of atoms per unit cell. Yani how many atoms are there in one unit cell, which we want to deal with. Of course, we are going to deal with unit cells. We are not going to deal with the whole lattice, so that's why. Yes?
Time's up.
Okay, all right. Then we will stop here if the time is up, and we will continue on the crystal structure here. But anyways, we will. This is important. I don't want to rush into that, so that it is clear what is the meaning of that. Then we are going to look at the different crystal structure types. Any questions? Any questions, guys? No questions.
No, Doctor,
No
no
questions.
question.
Okay, I will stop the recording. So I will stop the recording. So I will stop the recording من هنا ثم نغلق